Have you ever wondered what makes a rubber band stretchy or a diamond super hard? It all comes down to the atoms and molecules inside them. For thousands of years, we've used materials just as we find them in nature, like wood, stone, and metal. Their properties are decided by their basic chemistry. But what if we could design materials from the ground up to do things that seem, honestly, impossible? That's where the magic of mechanical metamaterials begins. These aren't your everyday materials. Instead of depending on chemistry, their amazing abilities come from their structure. Think of them like super-powered Lego creations, where the way you stack the bricks is more important than what the bricks are made of. It's all about the design. So what makes these materials so special? Imagine a regular sponge. When you squeeze it, it gets thinner in the middle, right? That's how most materials behave. Mechanical metamaterials, however, are designed to break these rules. They are materials engineered to have properties not found in nature. By arranging tiny, intricate patterns of beams, hinges, and voids, scientists can control exactly how a material behaves when you push, pull, or twist it. This level of control opens up a whole new world of possibilities. It's like being a material architect, building in functions like strength, lightness, and flexibility in ways we've only dreamed of until now. The secret is all in the geometry, which is just a fancy word for shapes and patterns. Scientists design tiny, repeating structures, often at a microscopic level. It could be a honeycomb pattern, a network of tiny trusses, or even complex folded shapes inspired by the Japanese art of origami. When you assemble thousands or millions of these tiny structures together, the overall material starts to act in very strange and useful ways. The individual unit might be made of a simple plastic or metal, but when they work together as a team, they can become incredibly strong, ridiculously lightweight, or even absorb vibrations like a futuristic cushion. It's a beautiful example of the whole being greater than the sum of its parts. This is a huge shift from how we traditionally think about materials science. Before, if you wanted a stronger material, you might have to find a new alloy or a different chemical compound. Now, engineers can take a common material, like a polymer, and give it extraordinary new powers simply by redesigning its internal architecture. It's a revolutionary approach that blends physics, engineering, and computer design. We are no longer limited by the elements on the periodic table. Instead, our own imagination and creativity become the primary tools for discovering and creating the materials that will build the world of tomorrow. This is truly the next frontier in how we make things. So, how do scientists actually create these incredible materials? It all starts on a computer. Using powerful design software, engineers can dream up and test different tiny structures, which they call unit cells. These unit cells are the fundamental building blocks of the metamaterial. The goal is to design a cell that, when repeated over and over again, gives the final material a very specific, desired property. For example, they might design a cell with special hinges that allows it to fold in a unique way. By arranging these cells in a grid, the entire block of material will inherit that same folding ability, but on a much larger scale. It's a bit like programming a material to behave exactly how you want it to. This design process allows for some truly mind-bending properties. One of the most famous examples is an auxetic material. Remember that sponge that gets thinner when you stretch it? Well, an auxetic material does the complete opposite. When you pull on it, it actually gets thicker in the middle. This counterintuitive behavior comes from its internal structure, which might look like a series of interconnected, re-entrant honeycombs or bow tie shapes that expand sideways when pulled. This property is incredibly useful for creating things like advanced padding or smart filters that open their pores wider when stretched, making them perfect for specialized applications. Another fascinating area is the creation of ultralight, yet ultra-strong materials. Scientists have been inspired by natural structures, like the internal lattice of bone, to create materials that are mostly empty space. Imagine a structure that is 99% air but can still support a heavy weight. This is achieved by designing microscopic truss systems, like the intricate network of beams you see on a bridge or a tower, but shrunk down to an incredibly small scale. These materials, often called metallic microlattices, are so lightweight that a small piece can be balanced on top of a dandelion puff without crushing it, yet they are remarkably strong and resilient for their weight. The ability to manufacture these intricate designs is just as important as the designs themselves. For many years, these ideas were just theories because we couldn't actually build things with such fine detail. But now, thanks to advanced fabrication techniques like three-dimensional printing, especially processes like stereolithography and selective laser sintering. We can bring these digital blueprints to life. These machines can build objects layer by layer with microscopic precision, perfectly recreating the complex geometries needed for metamaterials. This technological leap has blown the doors wide open for experimentation, allowing scientists to quickly prototype and test new designs. Let's dive into some of the amazing types of mechanical metamaterials that scientists are exploring. Besides the auxetic materials that get fatter when stretched, there are also pentamode materials. These are sometimes called metafluids because they are designed to behave almost like a liquid, but in a solid form. They are extremely difficult to compress, just like water, but they are very easy to shear or change their shape. Imagine a solid block that you could push your finger through as if it were thick jelly, yet it could still support weight from above. This unique property comes from a structure of tapered struts connected by tiny points, making it strong in one way but weak in another, by design. Then there are materials with so-called negative properties, which sound like something from a science fiction movie. For example, scientists are working on materials with negative effective density. This doesn't mean they have anti-gravity, but it means they can behave as if they have negative mass when they accelerate. When you push them, they can accelerate towards you instead of away. This is achieved by embedding resonating structures inside the material that vibrate out of phase with the force being applied. While we aren't building floating cars with this just yet, this property could be amazing for absorbing vibrations or directing sound waves in very specific ways. Origami and kirigami, the Japanese arts of paper folding and cutting, have also become a huge source of inspiration. By applying these ancient principles to modern materials, engineers can create sheets that can transform from a flat, two-dimensional shape into a complex, three-dimensional structure with incredible properties. Think of a solar panel that can be folded down to the size of a book for launch and then unfold into a massive array in space. These origami-inspired metamaterials can be designed to be stiff in one configuration and flexible in another, making them perfect for deployable structures, adaptable robotics, and even medical implants that can be inserted in a compressed form. Perhaps one of the most exciting possibilities is creating materials that can manipulate waves, like sound or even light. This has led to the idea of acoustic or optical metamaterials. By designing structures with features smaller than the wavelength of the sound or light passing through them, scientists can bend these waves in unnatural ways. This is the science behind concepts like invisibility cloaks, which could steer light waves around an object, making it appear as if it isn't there. For sound, this could mean creating perfect soundproof rooms or directing ultrasonic waves for medical imaging with unprecedented clarity. It's all about controlling waves by controlling the structure of the material they travel through. So, where will we actually see these amazing materials in our daily lives? The possibilities are truly everywhere. One of the most promising areas is in safety equipment. Think about helmets, car bumpers, or protective gear for athletes. An auxetic material, which gets thicker at the point of impact, could offer far superior protection by drawing material in to absorb the shock. Instead of just crushing, the material would become denser and stronger, right where it's needed most. This could dramatically reduce injuries from impacts, making everything from football games to car rides much safer for everyone involved. It's a smart way to manage energy. In the worlds of aerospace and architecture, the push is always for materials that are both stronger and lighter. Ultralight lattice materials are perfect for this. Imagine building airplane wings or spacecraft components that are just as strong as solid metal but weigh a tiny fraction of the amount. This would save an enormous amount of fuel, making travel cheaper and more sustainable. In buildings, these materials could be used to create support structures that are incredibly resilient to earthquakes. They could be designed to absorb and dampen seismic waves, protecting the structure and the people inside from harm. The future of construction could be both lighter and safer. The impact of metamaterials also extends into the field of soft robotics and medical devices. Robots are often made of hard, rigid parts, but metamaterials allow us to create robots that are soft, flexible, and can move more like natural organisms. A robot made from a shape-changing origami structure could squeeze through a tiny crack and then expand to perform a task. In medicine, this could lead to better stents that can be easily inserted into an artery and then expand with precisely the right amount of force, or custom-fit orthopedic implants that are both lightweight and perfectly matched to a patient's bone structure for faster healing. This is why mechanical metamaterials are such an exciting field right now. We are just beginning to scratch the surface of what is possible when we combine clever design with advanced manufacturing. We are moving from being passive users of materials to being active designers of their fundamental properties. Every new design and every new discovery unlocks capabilities we never thought were possible, pushing the boundaries of engineering, medicine, and technology. The next generation of amazing inventions, from safer cars to revolutionary spacecraft, might just be built from materials that were designed, not discovered. The future is being engineered, one tiny lattice at a time.